So, welcome back after a long and painful illness, as someone put it, and to this new video. I wonder if I can still talk on video. I've limited myself to a few live streams lately because I started doing things instead of just talking about them, which takes a lot of time and effort. The result, the 24 hours are pending, so don't start making videos. But anyway, in this video we talk about transformers. We are talking about step-up transformers for MC cartridges, or rather the only reasonable way to use an MC cartridge on your turntable without throwing money out the window. I will try to maintain a very conversational approach to explain to you, to make you understand why the only way to use an MC cartridge is to use a transformer step-up, especially if you want to use quality MC cartridges. Using an active step-up, then we will see what an active step-up is, and perhaps it is not the best choice. As for the cartridges you use, let's call them that, it's fine, we don't need to address it. But when you want something more, the difference between an active step-up and a transformer step-up becomes absolutely unpredictable. First, we need to explain what MM and MC cartridges are. We will avoid the various hybrids with moving iron and so on, variable reluctance and so on. We will stick to two macro worlds, MM and MC, and those who are a bit more expert will forgive me here. But let's start with the basics because this video needs to be accessible to everyone. MM cartridges or moving magnet. These are cartridges in which the translation of the stylus movement into the electrical impulse in the cantilever happens in this way. The stylus, tracing the arc of your record groove, displaces a tiny magnet within the pole pieces of a winding composed of a very large quantity of turns. So the magnet moves, the magnetic field it generates varies in the air gap of this transducer of ours. A variable electromotive force is induced in the turns filled around this transduction body, which reflects the tendency of the signal within the reached limits. If we enormously increase the number of turns, we can get a sufficiently high signal. Sufficiently high means that an MM cartridge typically presents an output level under standard conditions of 5 millivolts, which is a very low level. Considering that normally a standard line level is now a few volts, it should be 2 volts actually. Very often DACs and digital sources have very high levels, yes, 4 or 5 volts, etc. So the output signal of a high-level cartridge is still a signal 1,000 times lower than a line signal. That's why you use a phono preamplifier, right? To go from these 5 millivolts to the volts of the line signal and then apply the correction, but that's part of another video. Obviously, let's stick to what comes first. Moving on to MC cartridges, the transduction mechanism is configured in the reverse orientation. There is a fixed permanent magnet, usually very powerful, and the transduction coils are mechanically connected to the cantilever that carries the stylus. So the stylus moves, it moves the cantilever. At this point, the cantilever moves the coils in a fixed magnetic field. The magnetic field encountered by the coils will change precisely due to the alteration in the coil's position, is that correct? Due to the movement of the coils, an electrical signal is generated, again an induced electromotive force, due to the change in the magnetic field seen by the transduction coils. However, clearly, since these coils are attached to the part that moves the head, they must be very small because they need to be light. I cannot put a large coil on the stylus, nothing moves anymore. I must use coils with few turns. Few turns result in the same low output level. A standard MC cartridge, as we might term it, typically exhibits an output level under standard testing conditions of 0.5 MV. There are heads that output with even lower levels, and then there are also things in hybrid, high-output MC heads. Let's forget about them. These are things that typically end up combining the defects of the two worlds. Let's leave the pure or classic or whatever we want to call them, and the pure classic MC with low level for later. Pros and cons. The advantages of the MC are clear, because making a cartridge that needs to be fixed, relatively large, with a relatively high number of turns, is quite simple. Making a cartridge that is typically as large as the tip of this ballpoint pen, which needs to be light, extremely precise, and requires high-level watchmaking work. Here, these are objects that are made under a microscope. In some cases, they cannot even be made by a machine. They are even made by hand, precisely because they must be very, very precise things. So the costs will clearly go up. What other costs will go up? The costs associated with the phono preamplifier, because boosting a 5-volt signal is complex, but amplifying a 0.5 millivolt signal presents significantly greater complexity. I can already anticipate the outcry from everyone saying, oh, but yes, but I have upgraded my operational level to one with very low noise, blah 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 blah. Okay. I won't go into what I've already said in other videos about using active amplifiers instead of transformers, but if you are really curious to know how these things work, you can go and watch other videos. Let's just say that, for the sake of brevity, to amplify a lower signal and therefore have a much higher amplification factor, we encounter more noise, more distortion, a rise in the quantity of cascaded amplification stages, resulting in the ultimate degradation of our subtle signal. The result is that we spent a lot of money on a beautiful MC cartridge. Let's listen to it. Are you a little better than him? No, MC cartridges are wonderfully better than him. We have to get there. How do we get there? We get there using a transformer, obviously. Why? Because our MC cartridges run on low voltage, but they have a big advantage. Having extremely small coils with few turns means their internal resistance is also very low. On one side, this greatly assists us concerning current losses, which will be substantially lower than those of an cartridge. And moreover, these cartridges can produce currents corresponding to their signal, obviously stronger than those that a cartridge can handle. The input impedances for M, which is the input impedance of a normal preamplifier, you know, are about 47,000 ohms. The input impedances for MC are much lower. They are hundreds of times lower. You go to a few hundred ohms, sometimes even 30 ohms to make them work because, as I said before, they are cartridges that work with very low voltages but can handle relatively high currents. Be careful. I am not talking about amperes. We are always talking about currents at voltage levels. An MC cartridge designed for very high output levels achieves this because it possesses substantial torque, a long coil structure, and also a high internal impedance, a very high DC resistance within the coil. If I match it to a low impedance, nothing will emerge. The poor thing perishes. The entire voltage signal is dissipated within the coil, meaning no output is achieved. This scenario benefits us because our transformers can convert our signal from a low voltage, high current signal into a high voltage, low current signal at no cost, meaning they don't need to be powered. After all, as I mentioned, high currents are not needed to power a stage. Even an M-head unit can manage that. Therefore, utilize a transformer with a set transformation ratio. Typically, you can use transformers with a 1:10 transformation ratio. What does that mean? It means that 1 volt applied at the input translates to 10 volts at the output when considering a generic signal. So our 0.5 millivolts become 5 millivolts. Pay attention, we are making a general case, so a standard 0.5 millivolts, M-head, etc. If we have cartridges with an even lower output level, say 0.2 millivolts, we can use a transformer, for example, with a transformation ratio of 1:20. Our 0.2 millivolts will become 4 millivolts. A signal level absolutely acceptable for a phono preamplifier. Someone who can bring this signal level up to the necessary voltage level to listen to it. Then with the line preamplifier, with the integrated amplifier, whatever you want. What is the beauty of this? The beauty of this is, as I have already said, but I want to repeat, is that the transformer allows us to bring all the power we have at the input to the output. That is, all the signal that comes out of my MC cartridge is returned to the output exactly as it is. It is not degraded, no power is wasted, and no distortion is introduced. The last 3 things I said are not true. They would be in a perfect world. In our world, a transformer can lose power, can create distortion, can do everything it shouldn't do. What is the problem? It is a matter of making the correct transformers, so that these 3 parameters are respected as much as possible. Do you already know what I want to say? Making transformers like this costs money. Making a 1.10 or 1.20 gain stage with a simple transistor is very simple and costs €1. Doing these things with a transformer is very complicated and costs hundreds or thousands of euros. What is the problem? Well, we just have to decide what listening quality we want. If we are happy with the mainstream, we take our active stage and live patiently. We don't worry about this. If we want a higher quality level, then we must use a transformer again. How much can an MC transformer cost? Well, given that there are certainly all kinds of transformers around the world, typically, a good MC transformer that starts doing its job decently costs at least 1,000 euros. From there, the situation can only get worse. What features define a high-quality transformer? The quality of the core, the quality of the windings, and the quality of the materials used. Evidently, with the standard 1,000 euros budget, what you can source commercially is good, but not excellent. Lastly, as you are aware, I have been diligently experimenting with step-up transformers. Thanks also to Lundell's collaboration, who supported me on some rather brilliant projects. I was able to do a series of things, and I was able to experiment in the field with some very interesting solutions. As you know, a correlation exists between the quality of a transformer and its physical size, because the larger the iron transformer, or its core structure, generally speaking, the more ideally it tends to perform with the signals we need to utilize. I said in general, because using cores that are too large can cause problems with signals that are too small, because certain cores are not good at low magnetization levels. So we should be cautious, but overly small choirs are also inadequate. Small choirs are used for being cheap and for frightening us. In short, they do their job, but perhaps they don't do it sublimely. Indeed, these are the MC transformers. You see, the size of the transformer, including the core, is only a few centimeters, just a few centimeters. These are higher quality transformers than what we conventionally defined as commercial transformers, costing €1,000, just to give you an idea. Even moving to cores of this size. This is a standard Lundell transformer I used for reference listening with others. It is a transformer that is already significant in terms of size, cost, amorphous cores, and some rather elaborate features. This unit is demonstrably superior to the initial transformer we examined previously. When we start reaching these core sizes for an MC transformer, we really start hearing different things because the fact of using such large forces, such large cores, allows us to work, as I said before, in extremely linear areas of core magnetization, so it allows us to enormously reduce distortions, to enormously reduce losses. We need to exercise caution as the windings increase in size. Attention must be paid to the lamination and the spacing to ensure excellent coupling between the primary and secondary windings. But these are still other problems. The most interesting project I'm working on is this. As you can see, we are talking about even larger cores. These cores are made of nanocrystalline material, therefore a very special, very expensive, very beautiful material, with a very high magnetic permeability. A very modern material compared to perhaps the permalloys and things like that that are used, that have been used, etc. And here we begin to think about large cores. The dynamics expressed by this type of transformer here are something completely different from what comes out here or there. But as usual, when I start doing things, I don't do what's already been done. At least if you work hard and spend a lot of money, create things that don't exist yet. It's not true that they don't exist. There are some Japanese craftsmen, as usual, who make MC transformers of that size, and they are very good, and cost tens of thousands of euros. Let's try to make things qualitatively comparable to those objects costing tens of thousands of euros, but without the €10,000 cost. What are the special features of these transformers? Well, we have already mentioned the cores, very large cores, cores with extremely linear magnetization characteristics, with great sensitivity to small signals, and then very, very short in length. What does this mean? It means minimizing the coupling losses. If I have a very long coupling wire, this very long coupling wire, which is necessarily very thin, will have its own resistance, and when we pass a signal inside a conductor that has a certain resistance, the signal is attenuated because that energy is dissipated as heat. If we manage to have a very short signal, the shortest possible, then the coupling losses will consequently be minimized. This is important because, remember, when we talk about MCs, we have very short signals in the phono stage. This precise factor is what grants us the dynamic range, that additional layer of information, and the lowest possible losses within the signal transmission. If we forget this function and generate losses in the transformer, then we have done something wrong. Clearly, it's not easy to process such small signals on large cores with signals that must become long wrapping around a very large iron core. So the challenge is to design signals that have good coupling, low losses, and a satisfactory transmission for a board, which means at least beyond 50 kHz. Just to give you an idea, if we take this small transformer that will clearly have many small signals and signals, here we have higher losses than those we have in this object here. Just to give you an idea of the approach needed when designing and building these things. It's clear, repeating myself, making this transformer is much easier than making this one. To arrive at a working version of these objects, one that functions well, it was necessary to work really hard on them, with many prototypes and significant development costs, let's say. So, after this introduction, merely to familiarize you slightly with the subject and the significance of the step-up transformer, the transformer MC, let's briefly see what the advantages are for which the MC step-up transformer is absolutely necessary for an MC cartridge. Let's say technically, as usual, as when we talk about transformers, the advantage is that all the energy generated by our phono cartridge, our electrical signal, is sent to our phono stage. It is transmitted without any distortion or losses, which, provided the transformer is well constructed, are entirely negligible. If we employ an active stage instead, you are certainly aware of the process involved when we amplify a signal. We are not transferring this signal, we are in fact using our transformer to take a power source. We are modulating it with our signal to have a function signal, in this case larger. Let me simplify this concept considerably. What is the consequence of this? It means that this signal here comes from the power source. That is, this signal here is no longer the signal of our signal. It is the signal that comes to us from the power source. A power force modulated by active devices in our transformer. What does that mean? We remove the boards, and I write Nelson Pass here, not my parent. Any active device that we put in the path of our signal, any active device that we use to amplify the signal, good or bad, will continue to generate noise and distortion. There is no way around this, it's just how it works, it's physics, okay? Yes, you should listen to people talking about extremely linear stages, extremely silent stages, etc. But this is all more or less nonsense said to define a circuit when needed. The point is, this circuit doesn't transfer energy here to here, but here to here, while our transformer transfers the whole energy of our input signal directly to the output, without a power force that causes noise no matter how well made, because we are still talking about fractions of a millisecond. Because the swing is high relative to the signal amplitude. If you have a nice cartridge and you really want to hear its sound, this is the way to go. This, it doesn't matter if it costs 100 euros or 100,000 euros, is a nice panacea for those who don't know how to make transformers or use them. It's a relatively inexpensive palliative, or rather, not a relatively inexpensive palliative to make you say, ah, the preamp I built for you can handle both MC cartridges. So, as far as a preamp is concerned, it is a relatively inexpensive palliative. I take my hat off to you, okay? But anyway, probably those who buy a 1,000 euro or 2,000 euro preamp won't put an MC cartridge in front of it. This almost never happens, because in that case, an inexpensive MC step-up transformer used instead of the internal active step-up makes a revolution. But if any of you have quality MC cartridges, then if you want to hear what comes out of the cartridge and not what the step-up is reinterpreting, the only solution is to get a very good step-up transformer. All this to say, I am working on this. Soon there will be step-up transformers 1, 2, 3. I don't know yet how many models and with what features the last ones will be. There will be step-up transformers that will finally let you do this beautiful thing here instead of this ugly thing here. And remember, every time you introduce a transformer instead of an active stage in your signal path, the swing in terms of realism, musicality, detail, or whatever, call it what you want, because all the positive characteristics of this sound will only be improved. What about the cable? Well, it must be a correctly made transformer. It doesn't matter if it's an MC transformer, an interstage transformer, an output transformer, an inline transformer, it doesn't do anything different. If it is made well, it will work very, very, very well. If it is made badly, well, we have wasted time because, as I am telling you, the problem with transformers, the only real problem with transformers, audio, which is why they are not used more often, is that you must know how to make them, and you must know how to use them. And I assure you, after looking at so much audio in my life, this is not something to take for granted. At this point, I await your questions in the comments below regarding MC transformers. I hope I have cleared up any doubt you may have. We will discuss this more if needed. If needed, I am here. Comment, leave a like, share the video, and let's see what happens. In the meantime, I bid you farewell, and see you in the next video.